Isosceles triangle ABC with AB equals AC is inscribed in circle omega. Let D be an arbitrary point inside BC such that BD is not equal to DC. Ray AD intersects omega again at E other than A. Point F other than E is chosen on omega such that angle DFE is equal to 90 degrees. Line FE intersects rays AB and AC at points X and Y respectively. Prove that angle XDE is equal to angle EDY. So the first thing we notice is how do we construct point F in the first place? Well, we have these points D and E here, and instead of all points X such or suppose W such that angle DXE is 90 degrees, is just a circle with diameter DE. So let's go ahead and draw that in. Now we have that drawn in, we can start working on the problem. It's kind of hard to show what angle XDE is equal to, and much harder to show that is equal to angle YDE just using normal angle chasing. So we suspect that normal angle chasing might not work here. So let's try using projective geometry. Recall from my last video on projective geometry that we can use the right angle bisector lemma, which states that if we construct the line through D perpendicular to DE, which is therefore perpendicular to AD, and we let it intersect at a point, suppose W, then if this is 90 degrees, all that we have to show is that the cross ratio WE with XY is equal to -1. And then we'd be done. So we have this circle here, ABC, and points X and Y. X lies on AB, Y lies on AC, E lies on AD. Why not project through A onto the circle? Doing so, if we let AW be this intersect at suppose point Z, then we reduce the problem to showing that BC with ZE is equal to -1. But now we suspect something quite interesting. We suspect that the angle AZD is equal to 90 degrees. So we conjecture that angle AZD is equal to 90 degrees. And given that we have this tangent to this circle here, in fact, WD is a tangent to the circle with diameter DE because it's a circle with diameter DE and it's perpendicular to DE. And we have this right angle here, and the same motivation that we use to construct this diameter here motivates us to construct the circle with diameter AD. So let's go ahead and construct that real quick. There we go. Now it's slightly obvious what to use here. Like, suppose that the circle with diameter 80 intersects at a point Z prime. Then we wish to show that AZ prime and W are collinear. In other words, that AZ prime be or the line through D perpendicular to AD and EF concur. And given that there are 3 circles in the diagram, this really calls for the radical center theorem. Indeed, the radical axis of these 2 circles here is AZ prime, the radical axis of these 2 circles here is EF, and the radical axis of these 2 circles here is just the line through D perpendicular to AD, because both are tangent and have diameter on the line AD. Therefore, they all concur at the same point W, and therefore, the angle AZD is indeed 90 degrees. Now we've shown that angle AZD is equal to 90 degrees. And now that means that the points W, X, F, and Y are irrelevant for the problem because we projected through A onto the big circle omega. This means we reduce the problem to the following. Inside the following figure, if ABC is isosceles and points D and E are on the BC and the circumcircle, and we let AD, the circle with diameter AD, intersect the big circle again at Z, all that we have to do is show that in this case, BCZE is equal to -1. So how do we do this? Well, we have the points B, C, and then E. Well, we have the point D here, and E lies on line AD, and D lies on line BC. So we might want to try projecting through D onto the same circle. Recall from my last video that we can do that. So when we do so, we end up getting, after projecting, we get CB. Z gets mapped to a point, suppose, let's go ahead and let this intersect at some point, say Q. Then Q and E gets sent to A is equal to -1. And since harmonic conjugates are unique, that means that Q must be some unique point. Because this is ABC is isosceles, Q must be the point diametrically opposite A. So that means we want to show that if Q is a point diametrically opposite A, then ZD Q prime, where Q prime is the opposite point, are collinear. And this is where the right angle comes into play. We have angle AZD is 90 degrees. However, because Q prime is diametrically opposite A, we have angle AZQ prime is equal to 90 degrees as well. Therefore, DZ and Q prime are collinear, and we have thus solved the problem by projecting through D and getting this cross ratio as needed. We prove that these two angles are equal, not using traditional methods like angle chasing, but instead using a more powerful technique called projective geometry that I discussed in the past video. And using that, and using a couple projections and the radical center theorem, we were able to reduce the problem to a simple projective geometry problem that we ended up solving quite easily. So thank you so much for watching this video. Please subscribe if you'd like to see more.